And then I'd like to present a few slides about the need to measure ultrafine particles. So the first need is because now it's established in the directive, no? As exposed previously by Xavier. So in the directive, established that we need to implement supersites for measuring these novel metrics of emerging concern, such as black carbon, elemental carbon, oxidative potential, and ultrafine particles. And also in the case of ultrafine particles, it established that it's necessary to measure at hotspots, mainly related to traffic hotspots, such as city roads, airports, and ports, or in areas with high concentrations of ultrafine. So the first thing is, what is ultrafine particle? Ultrafine particles means particles with a diameter, according to the directive, less than or equal to 100 nanometers. But the most important is that here is established that we have to measure particles with a lower limit of 10 nanometers. And as we'll see, this is very important because depending on the lower limit, the number concentration of particles may vary considerably. And another thing that is clearly stated in the directive is that it's very important to use standardized measurement techniques. If there are standards or protocols, we have to use these standards, but if no, other methods can be used. But another need of measuring ultrafine particles is related to the fact that the current directive, the current limit values regulating concentrations of some pollutants, such as, for example, atmospheric particulate matter, do not permit to control, to monitor the real impact of this pollutant, of atmospheric particulate. PM is a complex pollutant. It's a solid and a liquid heterogeneous material suspended in the atmosphere that can be emitted by a variety of sources. It can be emitted as primary particles, but it can be formed as secondary particles. So there's particles that are formed from gaseous precursors. Also, there is a wide variety of sources, natural and anthropic. And this variety of sources and processes results in a wide variety of components, and most important, in a wide variety of size range. The particles can range from 2 nanometers to 20 micrometers. Here in this scanning electron microscopy images, you can see different compounds, different PM components. For example, this is a pollen. This is 1 micrometer, so this is a pollen, a biogenic particle of natural origin. In the center, this is 10 nanometers, and this has particles of sodium chloride. This is spray. This is marine aerosol. And on the right, this is 10 micrometers. This is mineral particles emitted in the desert dust in Sahara and collected in Barcelona. So there are coarse particles, but if you see here, these are particles that are totally different. On the left, this is 500 nanometers. This is a metallic particle emitted by a smelter. In the center, there is fly ash particles, the rounded particles, and this is ammonium sulfate. So that means primary particles and secondary particles emitted by a coal power plant. And on the right, you can see these very small particles. This is 20 nanometers. That is soot. That is elemental carbon or black carbon. So the important thing is, if we compare these particles, the pollen is comparable to a stadium, a football stadium, but the soot particles are comparable to a ball. So the range of sizes is very, very different. But the composition is the same. It's the same because both are composed by carbon. So this is organic carbon, and this is elemental carbon. So if we look to the size distribution of PM mass, that this is the regulated parameter currently by the European directive, we can see that the particles are concentrated in the sizes higher than 100 nanometers. So PM10 is the mass of the particles lower than 10 micrometers. These particles are mainly generated, the coarser particles, by mechanical processes or by evaporation processes, and the finer particles are emitted by combustion processes, and maybe primary and secondary. But if we look to the number of particles, we can see that the distribution is totally different. So the number of particles is concentrated in the finer section, so in the range lower than 100 nanometers. That means that if we are measuring only the PM mass, we are not controlling the particles lower than 100 nanometers. And these particles are the particles that probably may have a higher effect on health because they are thinner and they can go deeper in our body. So these fine particles can be produced by different processes, for example, nucleation, the particles lower than 20 nanometers, directly emitted by a vehicle exhaust emissions, or secondary formed by a new particle formation, the ATMO, so the accumulation. So there are different processes. But these different processes result in different composition. So the coarser particles formed by evaporation or by mechanical processes are mainly composed of mineral particles or marine aerosol. Also, there are nitrates, organic sulfates. But the finer particles are mainly composed of carbonaceous particles. So the message is that the measurement of the mass does not allow to control the ultrafine particles, and also we can say that the carbonaceous compounds are of great interest because they are accumulated in the finer fraction. Then this is a study that we are performing now in RI-URBANS in the pilot cities on health. And if we apply PMF statistical methods to apportion the contribution of the different sources to the PM10 mass, we can see that there are different sources. So there are the dust, the sea salt, the nitrate, the icy salt, the traffic, primary biogenic, sulfur-rich, so secondary oxidation, biomass. There are a variety of sources. But if we apply this method, this PMF, to the particle number concentration, we can see that the sources contributing to the number of particles is totally different to the sources contributing to mass. So here, more than 60% of the number of ultrafine particles is related to the emissions on traffic. So different sources, different composition affecting PM and ultrafine particles, and therefore they may have different effects. I'd like to show you, this is a study that we performed in 2011, that we studied this dial cycle of ultrafine particles in red and black carbon in black in 6 cities in Europe. And as you can see, there are differences. So, for example, in these cities, in London, in Lugano, in Bern, the dial cycle of number of ultrafine particles is very similar to the dial cycle of black carbon. So that means that probably both variables are emitted by the same source, that is traffic. If we go to Barcelona, Huelva, and Santa Cruz of Tenerife, we can see that there are differences. So the black carbon is peaking in the rush hours, and the ultrafine particles also, they show these peaks at the rush hours, but they show an additional peak at midday that is a different source that is related to photonucleation. So we perform a study in these 3 cities, in Barcelona, Huelva, and Santa Cruz, and we apply this method proposed by Rodríguez y Cuevas. And then this is the distribution, the dial cycle of the number of ultrafine particles, and we decompose in 2. By comparison with the black carbon, we decompose to N1, that is the primary particles emitted by traffic, and N2 in red, that these are the secondary particles formed by photonucleation. Then we perform an epidemiological study, and we compare the number concentration of these 2 modes, N1, the primary particles, and secondary particles, to mortality in the 3 cities. And the results were different. So in Barcelona, we identified that it was a correlation between the primary particles, the particles emitted by traffic, with mortality. So it was an impact of primary particles related to traffic emission. In Santa Cruz of Tenerife, in the Canary Islands, they was not impact. So the number of concentration of particles was different also in the 3 cities. But in Huelva, the impact was opposite to Barcelona. So it was not impact for primary particles, but it was impact for the secondary particles. Because in this case, the secondary particles were related to the transport by the breeze of the precursors emitted in an industrial estate southwest of Huelva, and the breeze transported these precursors that were oxidized and forming ultrafine particles, increasing activity. So the pattern and origin of ultrafine particles determines the short-term effect on humanity. We perform in RI-URBANS, this is my last slide, we perform a study and we compile all the data available measuring ultrafine particles, particle number concentration, and particle number size distribution in urban areas in Europe. We compile data from more than 29 sites. Here you can see the urban sites that we collected the data, and here you can see for each site what is or what was the size range measured by each instrument. As you can see, for the upper limit, there is no difference, but for the lower limit, there is a clear difference. For example, in Helsinki, they were measuring from 3 nanometers. In some places, were measuring from 10 nanometers as requested by the directive, but in other places, they were measuring 20 nanometers. If you remember the graph of the size distribution of the number of particles, this difference measuring from 3 nanometers to 20 nanometers may have a clear impact on the number concentration. So the current ultrafine particles measurements, or the measurements that don't perform it till now in Europe, are not fully comprehended. And there is an urgent need to harmonize measurements of ultrafine particles, particle number concentration, and particle number size distribution, also making the data open. And this is I think this is now issues because there are standards available and there are different guidance available. And I give the floor to Jacob. They will present which are the methodologies that are recommended for measuring these particle number concentrations, particle numbers.